our last presentation, we explained how the relationships that we obtain from the harmonic gauge, in particular this, reduces the number of the 10 independent components of the polarization tensor from 10 to 6. That's by just cutting down that number of components by 4. And so today we just want to show how, especially with a specific example. Again, I have to say right from the beginning at this moment that this is all thanks to Steven Weinberg's book on gravitation and cosmological principle. And also, sometimes around this year, 2020, about a few weeks ago, he released a text on lectures on astrophysics. And on that, in that book, he had a section summarizing gravitational radiation, which I believe will be very helpful for anyone who desires to understand gravitational waves and radiations. Okay, so moving on. Supposing our wave is propagating in the 3 directions such that the wave number just at the same time occur, the temporal component is also equal to k but non-zero, is greater than 0. And it therefore means that k1 and k2, the direction in the wave propagation in these directions is 0. So starting with our relationship then, which we obtained in our last presentation, we have in particular that k mu is equal, okay, well, this is just to say that we are still raising and lowering indices using the Minkowski metric. And so the relationship that we obtained from the harmonic gauge was that. And now we can write this also, which is this relationship. In other words, on the left-hand side, I have raised the mu in our usual method and lowered the mu here. Just by using whatever Minkowski metric I like to raise this mu. I can use that same metric to lower this mu. Of course, in the end, by the process of my raising and lowering, I may get some different index, which I can rename mu all over again because it's a dummy index. Now, on the right-hand side, I can rewrite this k nu as that, because as you can see, if I simply use this Minkowski metric to lower the mu, it becomes k nu. And so, as you can see at this moment, this is the same thing as written as being equal to that, because the E sigma as we have here could also be written as that by just lowering the sigma using another Minkowski metric. So, and one thing I can do, as you can see from the left-hand side, this will be equal to the sum. I'm trying to sum over mu. So I have for the first term 0, 0 in our characteristic where everything else remaining the same plus. Of course, what I will have to do next would be to say 1, 1 here plus 2, 2 plus 3, 3. I just try to make all that succinct by just representing all that by I here, which of course we know will mean summing over I. Now, if we look at this relationship, and I consider the case for which nu is equal to 1, I can do that. Nu is a free index. So, but if I set that to be 1 on the left-hand side, it becomes 1 everywhere on the right-hand side. And by that, of course, we know that the Minkowski metric, the one we're using, is a diagonal matrix. And so this is 0. And because this is 0, this whole term is 0. And what we're left with is just that. And at this moment in time, I has to be equal to I, otherwise, equal to 1, otherwise it's 0. For any other value of I that is not 1, this whole term is 0. So we set I equal to 1. And this, of course, is equal to 1. And K1, however, we knew right from the beginning, K1 is equal to 0. And since it is 0, then it means that this whole term that we've calculated is equal to 0. Now, supposing we replace nu with 2, then again, just like we did the first time, replacing nu all over the place with 2, we have again this, since it's not diagonal, it has to be 0. And then again, I have I2 here and Ki. Of course, at the moment, I will have to be equal to 2, otherwise, again, this is all 0. And then since eta 2 is equal to 1, however, again, we have a problem because K2 also is 0. And so because of that, this whole expression on the left-hand side is also equal to 0, since K2 is 0. Now, if we were to repeat this for nu equal to 3, for nu equal to 3, again, we get some non-diagonal term here due to this Minkowski metric, and so this is 0. And then again, I will have to be equal to 3 for this to be non-zero. So I being equal to 3, we have that eta 20 will be equal to 1. K3, on the other hand, is equal to K0 and is equal to K, is non-zero. And so what we have is that this particular expression is equal to half K and whatever it is that we have in this bracket. Since K3 is equal to K. Now, for the last one, supposing nu is equal to 0, again starting from this expression, if nu is equal to 0, then of course I have half eta 0, 0, K0 here, and then plus eta I3 K3. Sorry, Ki. However, we know that the I here can only range from 1 to 3. I cannot be equal to 0, so this particular term here is 0. Eta 3, eta naught naught is equal to minus 1. And that is why what I have here, for instance, is minus 1 all over, minus 1 K naught, eta sigma rho, E sigma rho. And then the K naught, by the way, is equal to K, and it's not 0, and that is why we have this to be equal to this. And of course, like we said, eta is not 0, eta naught naught is minus 1, and K naught is equal to K. So summarizing, we have just obtained that K mu E mu 1 is equal to K mu E mu 2 equal to 0. We've obtained K mu E mu 3 to be equal to that, and K mu E mu 0 to be equal to minus half K, eta sigma rho that. And all this was with the specification that K1 and K2 are 0, and then K3, K0 are non-zero. Now, looking at the first relationship that we obtained, that this is equal to 0, we can now work on the left-hand side by summing over mu again, and that will give us 0, 0, E1 plus 1, 1, E1, 1 plus 2, 2, So I'm just summing over the mu wherever we have mu. So I'm going to have 0, 0, 1, 1, 2, 2, 3, 3. And of course, the one that was here remains all along and is not changing. But then again, we said that K1 is equal to K2 and they are all equal to 0. So these two middle terms are 0 because of the presence of the K1 and K2. And what we are left with in the end is this first and last term. But then K0 and K3 are both equal to K. So I can pull that out of the bracket. And I'm left with just E0 1 plus E3 1. With the whole thing being equal to 0. And of course, K is greater than 0 here, is not equal to 0, so I must have whatever is left in the bracket to be equal to 0. Similarly, of course, for the next expression, this being equal to 0, of course, if I were to perform a similar expansion as I did here, I'll be left with only K0 and K3 with the factors following them, the K1 and K2 with their factors becoming 0 because of this condition. Again, this and this are equal to K. I pull them out and I'm left with this, and the whole thing is still equal to 0. K is not 0, so I must be left with this being equal to 0. At this point, I move on again to this next term. Okay, so I'm going to try to make things a little easier. Of course, on the left-hand side, we know that K2 and K1 are 0, so the expansion of this left-hand side will be K0 E0 3 plus K3 E3 3. And this is equal to here on the right-hand side. Okay, so the two are the same. I pull them out. And then I have E0 3 3, E3 3. Now then I have here equal to half K, just like I had here. And so what I can do here, well, I can try to pull them out, but then I can simply cancel out the K's. So that what I have in the end, after cancellation, as you can see, I'm sorry, somehow I had to include that. After cancellation, all I have is this to be equal to that. And the same thing, of course, occurs here. I have this whole thing on the left-hand side after expanding, because K2 and K1 are 0. So by the same saying, mu naught here, so naught plus 1, 1, 2, 2, and 3, 3. We are left with just the first and last terms. This is equal to minus half of K. Well, I'm sorry to have put the naught here. We've changed that long ago to K. Minus half of this equal to minus half of that. And again, of course, this should cancel that one. Okay, so as it is now, like I said, okay, so we've just rectified that. This K here has been cancelled by this common K. And so I have this to be equal to half that. Now, looking at the next thing, you can see also that for K mu naught here, which is the expression we obtained from this one, we have that the whole thing, of course, on the left-hand side, if we perform the expansion, we have these two, which are just the same, and I have minus half K here. So this, by the way, cancels the K here. And so in the end, I shouldn't have another K here, so I'm sorry again for that. At this moment, what we want to do is to find a way by which we can try to expand these two expressions. What we have here, for instance, is the fact that eta sigma rho, E sigma rho, should be expanded first of all in the first step. I will have to sum over sigma or rho, whichever one I choose. At this moment, I have chosen to sum over sigma. So what I have now is this, naught plus 1, 1 plus 2, 2 plus 3, 3. Now again, but the first term here could be summed again over rho, and this will produce the next 4 terms, just like I had 4 terms initially. I'll have naught for rho, 1, 1, and I have 2, 2, and 3, 3. So these first 4 terms, for instance, is just for this one. So I'm supposed to have plus again, performing the same thing for this, and that, and all over till I get to the last term. But all this is not necessary because the Minkowski metric is a diagonal metric. And so, eta 0, 1 are both equal to 1, 0, or eta, just know that for all the non-diagonal terms, you get them all to be equal to 0. And we want to note also that eta naught naught is equal to minus 1, like we've said before, and eta 1, 1 is equal to 1. And this for I here, sorry, eta I equal to 1, for I equal to 1, 2, 3. And so it means that if I want to expand this, it is okay to just go straight forward in writing that is equal to eta naught naught each 0, 0 plus this, plus that, plus that. And these are 4 terms, as you can see. And making use of these specifications that we have here right now, we are going to have that this is going to give us minus 1, and this 1, 2, 3 all give us 1. So that in the end, this expression is simply just equal to that. Okay, so having obtained already what we stated about our expansion for eta sigma, E sigma rho, as you can see, both this and this, also this had a minus sign. Well, I can pull this minus sign to the side or the left-hand side, and this will be what I get. As you can see, of course, we already expanded what is inside the bracket to be that. And the first one, of course, we will expand to this. Well, I can add these two expressions. From the left-hand side, you can see that this will be cancelling that because of the minus sign. Then I'll be left with E sub 3, 3 minus E sub naught naught on the left-hand side equal to, adding this to this is all the same, and so I just get one of those and not half as we have on both sides. Now, as we can see already, if we were to perform this operation, E3, 3 will cancel this one, and it has a minus here and a minus here. When I move it to the other side, it takes a plus sign, and so they cancel. I'm left with E sub 1, 1 plus E sub 2, 2 then equal to 0, which will imply this, that E sub 1, 1 is equal to minus E sub 2, 2. Now, of course, looking at the first expression here also, and if I were to make use of this expression, then it means that this first two terms here in that expression is 0. And so I'll be left with E sub 0, 3 plus E sub 3, 3 to be equal to just these last two terms here. So half of them. And so if I were to move this, which is 1, if it were to move to the other side, it would take a minus 1. So half of this minus 1 of those gives me a minus sign. So the minus sign now is a property for both terms in that expression. And so recalling also that we have originally obtained E sub 0, 2 plus E sub 3, 2 equal to 0, and E sub 0, 1 plus E sub 3, 1 equal to 0, then we have in general, or summarily, then E sub just, of course, making this a subject of the formula in this expression, and making E sub 0 to the subject of formula here. And we already obtained E sub 0, 3 from this expression. This is what we get. And then finally, we have E sub 2, 2 to be equal to E sub 1, 1 from this expression. Now you can see that we have been able to write about E sub 0i, the I there representing 1, 2, 3. And so we have about 3 components here, and 1 E sub 2, 2, and that's 4 components. We have been able to write these 4 components in terms of the remaining 6 components of the polarization tensor. And so from these transformations, you can see, of course, the ones that we talked about very well in detail in our last presentation. You can see from this transformation that the remaining 6 independent components transform according to this, which again we mentioned in the last presentation. And so if I were to choose both mu and nu to be 1, then I will have to do that all across the expression. But K1 is 0, and so we can see that E1 prime prime is just equal to E1 1. And so if I were to do that for E1 3, of course, using the same expression here that we have just made mention of, that's this particular expression. If I were to do that for 1, 3, so wherever I see nu, mu, I put 1. Wherever I see nu, I put 3. I repeat that all across the expression. I do the same thing for when mu and nu are 3, 3. I repeat that for when mu is 1 and nu is 2. I repeat that for when mu is 2 and nu is 3, and then for when both are 0, 0. And of course, when I do that, you can see that K1 is 0 here. K1 is 0 again. K2 is 0. K2 is 0. And the only things here that are non-zero are K3 and the K0s. As we have said before, these two are non-zero and they're both equal to K. This is something we have used at least 3 times now. Okay, now, so making that identification that K3 is equal to K, I can write this one here to be equal to that. And what is left of this expression becomes twice of this, and so it's just 2K epsilon 3. And the same thing here with this expression. Of course, these two are 0, so it means that E1 2 prime is just equal to that, and this is what I obtained. And so, of course, the same is applicable to this one and to this one. Of course, these two are non-zeros, and they are both equal to K. So I have twice of K epsilon naught plus E sub naught naught. And so, in summary, we have written them all in this form. And so we have all these 6 components. And then here you can see that only these two here that are written are not changed by coordinate transformations. So even though we transform them, they remain just this. And this falls in line with our explanation that we have just two physically relevant components for the polarization tensor. But then, of course, if you recall, these other ones here that are changed by this transformation, we could, as a matter of fact, send them to 0 after transforming them by just making the following tricky transformation. You can see if I were to set epsilon sub 1 here to be equal to, if epsilon sub 1 were to be minus, say epsilon sub 1 3 all over K, if I substitute that here, you can see that the K will cancel that. Then it will be left with E sub 1 3 minus E sub 1 3, and that will be 0. Now, by the same trick, if I were to change this E sub 3 here to minus E sub 3 3 over 2K, then the 2Ks will cancel. Then I'll be left with E sub 3 3 minus that, and this will give me 0. Similarly for this and this for the remaining 2 expressions. So we can set them all equal to 0 by our mere coordinate transformations. That did not happen and cannot happen for the 2 physically relevant components of the polarization tensor. So at this then, I think it is time for us to wrap it all up in talking about the components of the polarization tensor.